Welcome students. Today we will study the chapter of current electricity. With Ohm's law, we can find out the current through the circuit if the voltage across the circuit is known and the resistance of the circuit is known. But Ohm's law is insufficient to calculate currents and voltages in complicated circuits containing more than two energy sources and current carrying branches. Thus, we are going to learn two very important laws known as Kirchoff's laws. The first law is called Kirchoff's current law, that is KCL. It is also known as junction law. The statement of the law is like this: algebraic sum of the currents flowing through any node is always 0. That is, sigma I is equal to 0. Node is a point where more than two connections meet. It is also known as junction. For verification of this law, following convention is used. The first, the currents flowing towards the node are considered positive. And number two, the currents leaving or moving away from the node are considered negative. The figure shows node N where 5 connections are meeting. The currents I1 and I2 are approaching the junction, and the currents I3, I4 and I5 are leaving the junction. According to the convention, I1 and I2 are positive and I3, I4, I5 are negative. According to KCL, the algebraic sum of these currents is 0. That is, I1 plus I2 minus I3 minus I4 minus I5 is equal to 0. Therefore, I1 plus I2 is equal to I3 plus I4 plus I5. The law can be justified on the basis of law of conservation of charge. We know that current is the amount of charge flowing in 1 second. So, I1 plus I2 is the amount of charge approaching the node in 1 second, and I3 plus I4 plus I5 is the amount of charge leaving the junction in 1 second. As the junction or the node N is neither dissipating nor adding the charge approaching and leaving the node is same. That is, I1 plus I2 is same as I3 plus I4 plus I5, or I1 plus I2 minus I3 minus I4 minus I5 is equal to 0. That is, sigma I is equal to 0. Hence, the law is proved. The second law is called Kirchoff's voltage law, KVL, or the theorem of loop. The statement is like this: algebraic sum of the EMFs along any closed loop is equal to the sum of the products of currents and resistance in that part of the loop. That is, sigma E is equal to sigma IR. A network may contain many loops, but the law is applicable to any loop individually. To justify the law, like in the previous case, some convention is used. The first, current flowing in the same direction in which the loop is traced is considered positive. The current in the opposite direction is considered negative. The second, the EMF which tends to circulate current in the same direction in which the loop is traced is considered positive, and the EMF which tends to circulate current in the opposite direction is considered negative. The figure shows a network containing two cells of EMF E1 and E2 and 5 resistors of values R1, R2, R3, R4 and R5 respectively. The circuit contains 3 loops, that are A, B, C, D, E, F, A. The second one A, B, C, F, A, and the third one is F, C, D, E, F. Applying KVL for the loop A, B, C, D, E, F, A, we get minus E1 minus I1 R1 plus I2 R2 plus E2 plus I2 R3 minus I1 R4 is equal to 0. Therefore, E2 minus E1 is I1 into bracket R1 plus R4 minus I2 into bracket R2 plus R3. That is, sigma E is equal to sigma IR. The law can be justified on the basis of law of conservation of energy. EMF is the energy spent by the cell to circulate unit charge once through the entire loop. Product of current and resistance is the voltage across the resistor, which is the energy spent to circulate unit charge once through that resistor. Hence, LHS of the equation gives total amount of energy supplied by the cells, and RHS is the total amount of energy used by the loop. According to the law of conservation of energy, these energies are equal. That is, sigma E is equal to sigma IR. Hence, the law is proved. One of the important concept in this chapter is Whetstone's network. The figure shows a Whetstone's network composed of 4 resistors connected along 4 sides of rectangle ABCD. A cell of EMF E is connected across diagonal AC, and a center zero galvanometer is connected across another diagonal BD. Let I be the current drawn by the network. It splits into 2 parts, I1 and I2 at A. When the bridge is balanced, no current flows through the galvanometer. At this stage, following equation is obeyed. R1 upon R2 is equal to R3 upon R4. This is known as the balancing condition. If 3 out of these 4 resistors are known, the 4th can be calculated. The practical arrangement of Whetstone's network is known as Whetstone's bridge. As it uses 1 meter long wire, it is also known as meter bridge. It is used to measure unknown resistance. The figure shows the setup of the bridge. A meter long conducting wire PQ is fixed on a meter scale in stretched position between 2 thick aluminum strips A and C bent at right angles as shown in the figure. Another thick aluminum strip B is fixed between A and C such that it leaves 2 gaps, that are left gap between A and B and a right gap between B and C. A cell of EMF E, a plug key K are connected across the wire as shown. A rheostat is connected in series with the wire to adjust the current through it. Unknown resistance Rx is connected in the left gap and a variable resistance box Rb is connected in the right gap. One end of the center zero galvanometer is connected to B and its other end is connected to a sliding contact or a jockey through flexible wires. Then the circuit is made on and the null point is obtained. When the null point is obtained, the length PD is measured as Lx and length dq is measured as Lr. The resistance in the resistance box is measured as Rb, and now the unknown resistance Rx is obtained by the formula Rx is equal to Rb into Lx upon Lr. The experiment involves two errors. The wire may not be uniform in thickness along its length. Thus, it may be thin on the left side or thick on the right side. Thus, the sigma, that is resistance per unit length, may not be constant throughout the length. This introduces error in the result. And the second error is the contact resistance between the wire and the strips A and C play significant role in resistance measurement if the null point is obtained near P or Q. These errors cannot be eliminated. However, they can be minimized as follows. To minimize the first error, two sets of 3 readings are taken with the positions of Rx and Rb interchanged. That is, for first 3 readings, Rx is in the left gap and Rb is in the right gap. For next 3 readings, Rb is connected in the left gap and Rx is connected in the right gap. Thus, 6 readings are taken and average is calculated. To minimize the second error, resistance in the resistance box Rb is adjusted such that the null point is obtained approximately in the middle of the wire. Thus, resistance between PD or DQ is much larger than the contact resistance. Hence, the contact resistance can be eliminated. With the same setup, one can measure the resistance of the galvanometer. In this experiment, the galvanometer whose resistance is to be measured is connected in the left gap. But instead of null point, equal deflection point is obtained to assure the balancing condition. In the balancing condition, the length PD is measured as Lg and length dq is measured as Lr. Resistance in the resistance box is measured as Rb, and then the galvanometer resistance is calculated with the formula G is equal to Rb into Lg upon Lr. Same kind of errors are there in this experiment also, which are minimized by the same method. One more very important instrument we use in the laboratory is potentiometer. Let us study the principle of potentiometer. The figure shows a conducting wire AB connected across a cell of EMF E. If resistance of wire is R and its length is L, its resistance per unit length sigma is given as sigma is equal to R upon L, that is R is equal to sigma L. If the wire draws current I from the cell, it is given as I is equal to E upon R, or I is equal to E upon sigma L. Consider point C along AB such that length AC is L. Now resistance between A and C is sigma L. According to Ohm's law, potential difference between A and C is given as VAC is equal to I into RAC, but I is E upon sigma L and RAC is sigma into small l. Hence VAC is E upon sigma L into sigma small l. Hence it is E upon L into small l. As E and L are constant, VAC is proportional to small l. Thus, potential difference between A and C is directly proportional to distance of point C from A or length AC. As length AC increases, the potential of point C decreases and potential difference between A and C increases. The potential gradient is defined as decrease in potential of a point along the length of a wire per unit length of the wire. It is expressed in volt per meter. The principle of potentiometer is used to calculate EMF of a cell or to compare EMFs of two cells. The practical setup of a potentiometer is different than the setup which we studied to study the principle. The practical setup is shown in the figure. Very long conducting wire, typically of length 4 meter, 5 meter or even 10 meter, is stretched on a wooden board over meter scale between A and B as shown in the figure. A battery of large EMF E, typically of voltage 4 to 6 volt, is connected between A and B with a plug key K and rheostat RH in series. A cell whose EMF is to be compared is connected as shown in the figure, with its positive electrode connected to A and negative electrode connected to a jockey through a center zero galvanometer. In order to measure or compare the EMFs, following procedure is adopted. Plug the key and without jockey touching the wire, adjust sufficient current through the wire by wearing rheostat RH. Touch the jockey at different points between A and B and obtain null point D. Measure the length of the wire AD as L1. Replace the first cell by another whose EMF E2 is to be compared with E1. Repeat step 2 and obtain null point D. Measure the length of the wire AD dash as L2. Now, E1 can be calculated with the formula I sigma L1. E2 can be calculated by the formula I sigma L2, and E1 and E2 can be compared as E1 upon E2 is equal to L1 upon L2. It is not necessary that every time the cells should be connected separately. The method in which both the cells whose EMFs are to be compared are connected at a time is called sum and difference method. In sum connection, both the cells are connected as shown in the figure such that their EMFs are added to each other. So the connection is called sum connection. When the cells are connected in the circuit, null point is obtained at D. Length AD is measured as L1. In difference connection, the cells are connected as shown in the figure such that their EMFs oppose each other, and hence the connection is called difference connection. The cells are connected in the circuit and null point D dash is obtained. Length AD dash is measured as L2. From L1 and L2, the EMFs are compared with the formula E1 upon E2 is equal to L1 plus L2 upon L1 minus L2. The principle of potentiometer can be used to calculate internal resistance of the given cell. In the setup, a cell of EMF E is connected across the potentiometer wire AB with a plug key K1 and rheostat RH in series. The cell whose internal resistance is to be measured is connected as shown in the figure with its positive end connected to A and negative end connected to a jockey through a center zero galvanometer with flexible wire. A known resistance R in series with another plug key K2 are connected across this cell as shown. To measure the internal resistance, first key K2 is kept out of the socket and K1 is plugged. Without jockey touching the wire, sufficient current is adjusted through the potentiometer. Now, the jockey is touched at different points between A and B and null point D is obtained. Length AD is measured as L1. Then, the key K2 is plugged and step number 3 is repeated. So, null point D dash is obtained. Length AD dash is measured as L2. Then, by using the formula internal resistance small r is equal to R into bracket L1 minus L2 upon L2, the internal resistance of the cell is calculated. Now, altogether a new concept is introduced in the chapter, that is thermoelectricity and seeback effect. Electricity obtained from thermal energy is called thermoelectricity. The production of EMF in a closed circuit made up of two different metals due to temperature difference between two junctions of these metals is called thermoelectric effect or seeback effect. The closed circuit formed by connecting the ends of two wires of different metals is called a thermocouple. The EMF produced is called thermo EMF and the current produced is called thermoelectric current. Exactly opposite effect is also obtained, which is known as Peltier Effect. If a current is sent around a thermocouple of two junctions, heat is evolved at one junction and it is absorbed at the other junction. In antimony bismuth couple, as shown in the figure, when a cell is connected and current is passed, heat is evolved at the end where the current flows from antimony to bismuth and heat is absorbed at the junction where it flows from bismuth to antimony. When the direction of the current is reversed, the heating and cooling at the junction is also reversed. This shows that Peltier's effect is reversible. One more similar kind of effect is known as Thomson's effect. The absorption or evolution of heat along unequally heated conductor when an electric current is passed through it is called Thomson's effect. When different parts of a conductor are kept at different temperatures, an electric current is passed through it, heat is absorbed at some parts and it evolves at some other parts. When two ends of a copper rod are maintained at different temperatures and electric current is passed from hot end to cold end, heat is produced in the rod and the rod gets heated. On the other hand, if current is passed from cold end to hot end, heat is used and the rod gets cooled. This effect of evolution of heat when current is passed from hot end to cold end is called positive Thomson effect. Antimony, silver, zinc, cadmium, etc. also show positive Thomson effect. But the metals like iron, nickel, cobalt, platinum, bismuth, etc. show opposite effect. When the temperature difference is maintained at the two ends of an iron rod and electric current is passed from hot end to cold end, heat is utilized and the rod gets cooled. If the current is passed from cold end to hot end, the heat is produced and the rod becomes hot. This effect of absorption of heat when current is passed from hot end to cold end is called negative Thomson effect. The thermo EMF can be measured by using the principle of potentiometer, and the hot junction is heated to different temperatures and the corresponding thermo EMF is obtained. If the thermo EMF is plotted against temperature of the hot junction, provided that the cold junction is at 0 degrees Celsius, we get a curve of shape like inverted parabola. As it is used for calibration to determine any unknown temperature, it is called calibration curve. From the curve we can study two more definitions. Neutral temperature. The temperature of the hot junction for which the value of thermo EMF is maximum is called neutral temperature. In the figure, it is 270 degrees Celsius. Inversion temperature. The temperature of the hot junction beyond the neutral temperature at which the value of thermo EMF becomes 0 again is called inversion temperature. If the temperature of the hot junction is increased beyond this value, a thermo EMF of opposite polarity is produced. Generally, the inversion temperature is twice the neutral temperature provided the cold junction is at 0 degrees Celsius. There are many uses of thermocouple, but mainly it is used as a thermometer for measuring very high temperatures very accurately, and it is used for measurement of intensity of heat radiations. The instrument used is known as thermopile.